Well, thank you, Rick. Thank you all for serving this remarkable institution. I've been hanging out this week learning more about it and figuring out what we could be doing together. And I would like the opportunity, if you'll allow me, to rearrange your metal furniture a bit about design, where, like this handsome but rather puzzle-looking Sumatran fellow, I've been wandering in the bewilderness for the past 4 decades. I'd like to start by getting us all into beginner's mind, opening ourselves up to new ideas by stopping having old ideas. That's the hard part, as one of my mentors, the elder Edwin Land, used to say. So let me start with an example that's been in textbooks on creative thinking for decades, the 9 dots problem. And it's usually framed as find the solution that will connect these 9 dots with just 4 lines without lifting your pen from paper. So you're supposed to think 1, 2, 3, 4, oops, 5, that doesn't work. 1, 2, that isn't going to work. And what you're supposed to do is think outside the box, which is where that expression comes from. But one day, a Stanford student startled her professor by saying she just figured out how to do it in 3 lines. How do you do that? 4 was hard enough, and dots are infinitely small. Well, actually, these are rather plump dots, and it looks like you don't have to go through the middle of them. So if your paper is wide enough, you can do the Z for Zorro trick. And then seeing that, the students started to feel rather liberated, and they started to solve this problem in 1 line. There are a lot of great 1-line solutions. I'll just offer a few to get you started. We have Takeda Sensei and other Japanese guests here today who, of course, will first think of the origami method, where you fold up the paper until all the dots fall together in 1 line. Or if you're a geographer, you might use a very long line. Or if you're a tool-using critter, like a mechanical engineer, you could get out a tool called a scissors. There was no rule against cutting out the dots. Or if you're a statistician, you could just crumple up the paper, and if you stab it over and over again with the pencil, eventually you will go through all 9 dots at the same moment. The one I like best came from a 9-year-old girl who said, "You didn't say it had to be a thin line, so I used a really thick line." So, as the late Paul McCready said, this tyranny of the word "the," find the solution with 4 lines, puts us back in the box, the non-existent imaginary box we all think is there. And it keeps us from being more creative in finding elegantly frugal solutions. So, in the spirit of beginner's mind, in 1982, I had never before built a house, and I didn't know what was impossible, so that made things possible. So I did the conceptual and energy design for our owner-builder house, 2,200 meters up in the Rocky Mountains near Aspen, where the temperature used to go to minus 44 Celsius, minus 47 Fahrenheit. But this house does no combustion. That's so 20th century. In fact, it has no heating system, super insulation and ventilation heat recovery, and super windows that insulate like 16 sheets of glass but look like 2 and cost less than 3, made it 99% passive solar heating. But eliminating the heating system more than paid up front for the efficiency that displaced it. Construction cost went down. And how do you do that? Well, the textbooks say when you're insulating a house to use only as much insulation as will repay its extra cost over the years from the saved heating fuel, which sounds logical, but it's methodologically wrong because it leaves out the capital cost of the heating equipment. So I've used over twice the supposedly cost-effective level of insulation in order to eliminate the furnace, ducts, fans, pipes, pumps, wires, controls, and fuel supply arrangements, and therefore ended up with this 99% saving on space heat with an $1,100 lower construction cost. So I got not diminishing returns, but expanding returns to investment and efficiency. Now, if you come into the middle of the house in a February snowstorm, it looks like this. So far, we have grown 59 passive solar banana crops. In fact, we had twins last year. This 30-kilo crop up at the top, which harvested itself by pulling down the tree. In 1984, this house was saving 99% of its space and water heating energy, 90% of its electricity, all with a 10-month payback. Also, we saved half the water. Today's technologies are a lot better, so we've retrofitted them, and we're measuring 300 data streams to see how much better they are. The trouble is the lights and appliances are using less electricity than the monitoring system. This design approach works from Old Snowmass, Colorado to Bangkok, but wherever you are, the key is integrative design that gives you many benefits from each expenditure. So this white arch that holds up the middle of my house actually has 12 different functions, but it has only one cost. Design translates intent into artifacts, so design has to start with intent. And my design intent was to create delight when entering the building, and health and happiness and productivity when you're in it, and regret when you leave, and make it look like it grew there. One of the subsets of that intent was to keep people comfortable, and classically that depends on 6 variables. My design aimed at low air temperature, high mean radiant temperature, and medium humidity. That's healthier than hot, dry air. And I made the radiant and air temperatures out of phase by months so as to smooth out their average, which, other things being equal, defines your comfort sensation. Actually, for its first quarter century, this was a classic passive building which had no controls because there was nothing to control. The nearest thing we had to controls was operable windows. If it got too hot, you'd open the windows. If it got too cold, you'd close the windows. And either way, you'd equilibrate back to ASHRAE comfort. Now, most designers, though, think of energy efficiency as like picking individual cookies out of a jar. So if a cash-constrained real estate developer asked her architect, how can I make my new little office building more efficient and green, probably she'd be handed a list something like this of different things that could be added at a certain extra cost and annual saving at a simple payback period. And a cash-short developer would say, sorry, none of that pays back quick enough, none of those cookies is worth picking. But if instead she had chosen everything on the list, then the better daylighting and reduced internal heat gain would create a new ability to shift some windows around and shrink the mechanicals for smaller loads. So most of the extra costs of the efficiency would be offset by the capital costs they save, and the net cost, just over $4,000, would pay back in a year more quickly than any of the measures separately. So the whole, as Aristotle told us, is a lot more than the sum of the parts. And we've helped design over 1,000 buildings this way. Actually, my house helped inspire 40,000 passive houses and buildings that, like ours, have no heating and about normal construction cost. And such integrative design even works in retrofitting old buildings. That's how our 2010 retrofit is saving 2/5 of the energy in the Empire State Building. Remanufacturing its 6,514 windows on site into super windows that pass light through but block heat, plus better lights and office equipment and stuff, cut the maximum cooling load by 1/3, but then we could renovate smaller chillers instead of adding bigger chillers, saving $17 million of capital cost, thereby paying up front for most of the improvements and cutting the payback to 3 years, or under 1 year if we had counted non-energy benefits to owner and tenant. By the way, a major energy service company also offered a 3-year payback, but using disintegrated design with 6 times smaller savings, so thankfully they didn't get the job. Another big office retrofit we designed could even save 3/4 of the energy with a -5-month payback that is slightly cheaper than the normal 20-year renovation that saves nothing if you coordinated the two and did the right things in the right order at the right time. So how do you do that to achieve, say, summer comfort? How did our new office, nearing completion in nearby Basalt, Colorado, eliminate its heating and cooling equipment? Well, start with the comfort intent. Once in Japan, I asked my hostess, why don't you heat your house? And she said, why should I? Is the house cold? Emphasizing that the building has no nervous system and no comfort sensation, only people do. So we ought to be delivering comfort to people, analogous to task lighting, rather than to the whole space. and the structure. So in our new office building, each worker will have a hyperchair whose smartphone app or slider control uses 3 little computer fans or a pair of 7-watt electric car heaters, all run on a lithium battery, to deliver comfort to the occupant to match individual requirements, whereas when the Berkeley Comfort Experts recently surveyed 50,000 office workers, 42% of them felt thermally uncomfortable. I don't think we're going to have that problem. So we maintain ASHRAE comfort in indoor dry bulb temperatures not of like 21 plus or minus 1 Celsius, but from 18 to at least 30 by exploiting all 6 classical comfort variables through everything from excellent ceiling fans to super windows that block unwanted heat gain. So we rigorously reduce also the unwanted internal and external heat gains and recover 90% of the heat or cool in the outgoing ventilation air. And all this eliminates the boiler, the chiller, the pumps, and essentially all the fans, because the ventilation is natural. So in our cold climate, our building is in effect dressed in a down jacket and sunglasses. It's super insulated. It's more airtight than Passive House standard by factor 3 so far. It's passively cooled by active exterior shading and natural ventilation, including automated night flush to store cool in the phase change interior walls. So we didn't need 4 other kinds of non-refrigerative passive cooling. We didn't need active non-refrigerative cooling, evaporative, desiccant, absorption, ways to yield over 100 units of cooling per unit of electricity instead of the usual 3. We didn't need refrigerative cooling. We didn't need fancy storage and controls. And this comprehensive approach to summer comfort can save about 90 or 100%, 100 in our case, of cooling energy with better comfort, lower capital cost, and higher uptime anywhere in the world. But our understanding of integrated design keeps improving. The 38% energy saving in our Empire State Building retrofit seemed pretty good in 2010, until 3 years later, retrofitting this big federal complex in Denver, we got a 70% saving cost effectively, making this difficult half-century-old building more efficient than the best new office in the country, which in turn is only half as efficient as our own new office that we'll move into in December. And the technology didn't change. All this stuff was available over a decade ago. What changed was our improvement in design, how we combine and choose the technologies. And yet very few people think of design as a scaling vector. They just look for the latest new gizmo. These examples then illustrate how to start with the end-use effect you intend, based on understanding the people and culture you're working with, and optimize buildings as whole systems, not as a bunch of components. So the key to a cheaper to build as well as a cheaper to run building is to use expensive windows. And in particular, how to pay for the efficiency through the mechanical system shrinkage that it causes, and cut the most capital cost, as I'll explain in a minute, by saving from downstream to upstream, and then optimizing the sequence and the timing of the design steps. The prize is pretty big here. Tripling or quadrupling the energy productivity of the U.S. building stock by 2050 turns out to be able to save 4 times its cost. So it's worth $1.4 trillion net present value with a 33% internal rate of return. Details for that and other sectors in Reinventing Fire. Can we do the same trick with cars, the biggest user of oil? Well, a typical 7 or 8 liter per 100 kilometer mid-sized car nowadays emits each year its own mass in carbon dioxide, and it burns each day fuel derived from 100 times its mass in ancient plants, primeval swamp goo. The world runs on burning 4 cubic miles a year of primeval swamp goo, or its rotted remains. But did you know that less than 1% of the fuel energy you feed into your car actually moves the driver? Here's how that physics works. 7/8 of the fuel energy never reaches the wheels. It's lost in the engine, idling, driveline, and accessories. Of the 1/8 that does reach the wheels, called the tractive load, more than half is lost heating the air that the car pushes aside and heating the tires and road. And only the last 6% actually accelerates the vehicle and then heats the brakes when you stop. But only 1/20th of the mass you're accelerating is you. The other 19/20ths is the heavy steel car. So only about 0.3% of the fuel energy moves the driver. Not very gratifying after 1¼ centuries of devoted engineering effort. And yet automakers have long focused on wringing losses mainly out of the propulsion system, the red bar, because that's where the losses are. It's like somebody asked Willie Sutton, why do you rob banks? He said, because that's where the money is. Well, saving 1 unit of energy in the powertrain, the red stuff, saves 1 unit of fuel at the tank. But when you save 1 unit of tractive load at the wheels, that means you don't need to waste another 6 units of energy getting into the wheels. So you leverage 7 units of fuel savings at the tank. So first we ought to reduce the tractive load and then improve the powertrain, which can shrink to get the same acceleration, so you save capital costs to help pay for the lightweighting, just like shrinking mechanicals in buildings to pay for the efficiency that did the shrinking. For autos, weight causes 2/3 of the tractive load, so the top priority ought to be lightweighting. That's how RMI's fifth spinoff, Bright Automotive, got this aluminum fleet van to average 7 times the typical urban efficiency of today's steel vans. And unlike steel plug-in hybrids, this aluminum one could make a good business case with no subsidy because it weighs less with a ton of payload than its competitors weigh empty. So taking it out a ton of weight and a bunch of drag through NASCAR aerodynamics eliminated most of the costly batteries, making the whole thing affordable. Now, the same physics-based logic would suggest using even lighter and stronger materials like the carbon fiber composites used in aerospace and in race cars. Real automaking, though, needs about 1,000 times higher production volume and lower cost than in aerospace. But I gained hope that this gap might be bridgeable when I met a young engineer at the Lockheed Martin Skunk Works, Dave Taggart, who had led the design of a 95% carbon fiber advanced tactical fighter airframe that was 1/3 lighter but 2/3 cheaper than its 72% metal predecessor, because it was designed to be optimally makeable out of carbon, not metal. He couldn't find a military customer for something that radical, so he quit, and one bounce later I hired him to lead at RMI the complete virtual design of a half normal weight, 4 to 6 times more efficient carbon fiber SUV with about a 2-year payback, and it was called Revolution. We did that in 2000 with a couple of tier 1s. So this is a sporty active outdoor lifestyle crossover vehicle. Things like that were pretty novel then, but now it looks like a lot of things on the road. It can haul 5 adults in comfort, 2 cubic meters of cargo. If you fold down the right seats instead of the rear seats, you can put in 2 full-size kayaks and 2 adults. You steer and control it with a right or a left side stick, which you can easily plug in on the right instead. Near heads-up display, all functionality in software, computer with wheels, not a car with chips. It's basically a dream of a Tesla S 15 years ago. Way cool. Could be radar stealthy. And of course, to get rid of half or 2/3 of the weight, you have to optimize the whole vehicle as a system and go several times around the design cycle or design spiral, as we know from aerospace. Because less weight eliminates loads, reduces loads, and it shrinks structures. The less weight you have, the less weight you need. But you're not just decompounding mass by shrinking things, but also by getting rid of them, because as soon as you can afford, say, a good series hybrid, suddenly you no longer need the transmission, clutch, flywheel, axles, differential, U-joint, starter, alternator. A whole bunch of things go away. That saves more weight. Then you go around the spiral some more, making things even smaller and getting rid of more things. And by the time you get done, you have saved so much of the costly materials and the costly electric powertrain components like batteries or fuel cells, and so simplified manufacturing that you end up at roughly the cost you started with. The ultralighting becomes approximately free. But to achieve such results, You have to design in the future, not the past. Some of you will remember in 1960, the Soviet Union shot down Francis Gary Powers' U-2 spy plane, which had been designed at the Skunk Works. But Kelly Johnson there did not say, I'm going to design a little better U-2. He said, I want to own the skies for decades. Let's do a Blackbird. We don't know what happened, we'll figure it out. It took him about 13 months. Because he understood that you couldn't design an airplane like that within the conventional design space, because design is like a rubber band. If you stretch it from where you are now, you get more and more resistance and eventually it breaks. So if you want to do something completely different, you have to jump into that design space, and then you can stretch the rubber bands back as much as needed to accommodate technologies that aren't right yet. But as they mature, they will relax to where you want to be. Otherwise, you don't get there. And that's true of all kinds of design. But you also need a new design process. Dave Taggart was one of the keepers of the Kelly Johnson flame, and he brought to our hypercar project a radical way to organize people. Not the usual 1,000+ engineers designing individual pieces of a car and tossing their bit over the transom to the next specialist, but rather 7 engineers around the table, collectively tasked with formidable all-vehicle requirements, which the industry had no idea how to meet, but each also responsible for one specific vehicle system or function, for which, that's the sneaky part, we deliberately wrote no requirements, because we didn't want him to turn his problem into her problem. We wanted all 7 engineers to have to work the whole vehicle as one integrated design problem around the same table. 2 of the engineers were uncomfortable not having their very own requirements. We replaced them in the first week or 2. Then it worked fine, and we got this remarkable result. And then Toyota asked how we did it. We told them, and with results you'll see in a moment. Now, at least 4 to 7 automakers are already making the strategic shift to lightweighting plus electrification that we launched in '91, and then sped up 2 years later by open sourcing it like Linux, and getting everybody worried their competitors would do it first. So that leveraged our $3 million of soft money R&D into over $10 billion of industry commitments over the next 7 years. We like that kind of leverage. And now it's all over the place. Lightweighting and electrification are the 2 main strategic trends in the industry. Now, how's this going? You've just seen the Revolution SUV we did 15 years ago with a couple of Tier 1s. 7 years later, what Toyota did using the same method was this wonderful 1X concept car with the interior volume of a Prius, half the fuel use and 1/3 the weight, 420 kilos. And now, as of last year, both Volkswagen and BMW have carbon fiber electric cars on the market. And BMW confirmed that the carbon fiber in the i3 is paid for by needing fewer batteries. Now, we've commercialized in one of our spin-offs a breakthrough process for making big carbon fiber structures at Automotive cost and speed, paying for the ultralighting by a 2/3 smaller powertrain and radically simplified manufacturing using an airframe-like snap-together design. That turns out to reduce the investment required for automaking by about 80%. Now let's apply our buildings and vehicles lessons to industry, which uses half the world's energy and most of its motor power. 3/5 of the world's electricity runs motors. Half of that runs pumps and fans that move fluid from one place to another. And for pumping loops, the installer will typically place the tanks, boilers, and other stuff in convenient or traditional or arbitrary places, and then call in the pipe fitter to connect point A to point B. And engineering textbooks tell the pipe fitter to make the pipe only fat enough to repay its cost by saving pumping energy without counting the capital cost of the pumping equipment. We've heard this one before. And this method yields long, skinny pipes full of customary and easy-to-draw right-angle bends snaking around obstacles and driven by big, costly pumps. And the pipe fitters think this is just great because you pay by the hour. They mark up the extra fittings. They're not paying for your bigger pumping equipment or your bigger electric bill forever. How much bigger? Well, a typical industrial pumping loop was redesigned to use at least 86% less pumping energy, not by improving the pump's motors and controls, although that's all worth doing, but just by replacing long, thin, crooked pipes with fat, short, straight pipes. First, we lay out the pipes before the equipment, cutting friction 3 to 6-fold by using a straight shot, even if the pipe crosses the room diagonally or does a big sweeping bend or something else that looks weird. Next, the friction in a pipe falls as nearly the 5th power of its diameter. So we optimize diameter in a good design to save not just pumping energy, but also pumping equipment. Because the pump, the motor, the inverters, the electricals all have to be big enough to overcome the friction. And their size and roughly their capital cost will go down as nearly the 5th power of pipe diameter. But the capital cost of the fatter pipe will go up as only about the 2nd power of diameter. So when we conventionally optimize the pipe as a component, we are pessimizing the system. And in this case, we got an order of magnitude lower pumping energy, lower capital cost, and as a free bonus, we save 70 kilowatts of heat loss with a 2-month payback because it's a lot easier to insulate short straight pipes. Notice this is not a new technology. This is asking different design questions in a different order. But I later realized we had left out 8 additional benefits we should have counted, and had we done so, we'd have saved more like 98%. And indeed, in some new pipes in my house, we recently got a 97% saving. At California's Oakland Museum, to give you a practical example, our colleague Peter Rumsey retrofitted an efficient layout into the condenser water cooling loop. Notice the Y bends instead of right angle bends, sweet bend, pipe running diagonally through the air, looks pretty weird, saved 3/4 of the pumping energy with a 2 or 3 month payback, and eliminated 15 pumps, which will never again waste energy and maintenance costs. And then he repiped the chilled water loop and added variable frequency drives. That saved 85% of the energy and doubled the flow. To help the pipe fitters understand how to lay out pipes in this very unconventional way, he just said, lay out the supply pipes as if they were drains. Because the pipe fitters have another part of their brain that realizes drains have to be straight, because if they have bends, they clog, right? They run just on gravity. So what does all this mean for the electricity that's 3/5 used in motors? Well, from the fuel burned in the power plant to the end use, there are so many compounding losses that only 1/10 of the fuel energy you feed into the power plant actually comes out the pipe as flow. But if we now turn those compounding losses from left to right around backwards from right to left, then every unit of flow or friction we save in the pipe will compound back again to save 10 units of fuel and cost and pollution and global weirding back at the power plant. And it also shrink the equipment and the capital cost more than paying for the fatter pipes and greater thought. If we did that kind of systematic improvement to all the pipe and duct systems in the world, we'd save about 1/5 of the world's electricity, or half the coal-fired electricity, with retrofit paybacks typically under a year. So my team has applied this and many other kinds of integrated design to over $40 billion worth of industrial plants, with typical retrofit savings around 30 to 60% paying back in a few years, and in new designs more like 40 to 90 odd percent, with nearly always lower capital cost. The same logic also applies, my last example, to big data centers. 2/3 of the fuel you feed into the power plant is lost in the power plant and the grid before it gets to your meter. Of the electricity you pay for, half doesn't get to the servers because it's lost first in the cooling system and uninterruptible power supply that are half the total capital cost of the facility. Half the server energy doesn't get to the chips because it's lost in awful and usually very badly part-loaded power supplies, and a whole bunch of fans to take heat that largely shouldn't be there off the motherboard into the room so we can do dumb things with it. And then the next problem is severe underutilization of computing resources, partly through lack of virtualization, so there's one physical server per app even if it hasn't run for 10 years. Now the resulting little stem of energy flow down here is about to disappear, so let's magnify it. The next problem is bloatware, running a lot of unnecessary threads and processes, and making simple tasks very complicated because CPU cycles were cheaper than programmers' attention and someone else was buying the energy. Then downstream of all that, you may even have inefficient building processes, multiply it all out, and a few times 10 to the minus 5 of your fuel energy is actually emerging from the other end to create customer value. So where do we start to fix this problem? What end?
Right.
Downstream, at the right, yeah. So let's first of all, first you would fix the business processes if they're bad, and even if not, you would write elegantly terse code with the goal that every compute cycle is a needed and wanted one. And that becomes actually quite important with the shift to mobile devices, because that's going to stretch battery life, which is extremely valuable. Then we can at least quadruple the technical efficiency of the servers, more nowadays. And then the servers will need a lot less cooling and power supply, both of which can be done in much smarter ways than normal. And we could even cut in half the utility losses by using fuel cell trigeneration, and the total capital cost will go down. Multiply those savings from downstream to upstream, and you get at least 2, maybe 3 orders of magnitude energy savings. And in an actual project, data center in Britain, our partner EDS said that had our recommendations all been adopted by the client, we would have saved about 95% of the energy and half the capital cost. So I've given you examples from buildings, cars, pumping systems, and IT, a lot more. And all these examples showed how to design from downstream to upstream, shrinking or eliminating the upstream parts to pay for highly efficient downstream use. But thinking that energy efficient design is about choosing and installing energy efficient equipment is like supposing that if you just toss good ingredients in a pot and heat and stir, you'll get a wonderful dish. But actually, efficient systems like good cooking result from whole system design. Even the finest ingredients will not make a tasty dish unless we use a good recipe that the chef skillfully combines to get the right ingredients in there in the right sequence and manner and proportions. And often a good way to learn how to do that is to study nature. I trust you're all familiar with Janine Benyus's pioneering synthesis biomimicry and with resources like asknature.org. But now the founder of Pax Scientific, an Australian naturalist named Jay Harmon, who saves sea turtles, a sea captain, keen observer of nature, has developed a whole new kind of hydrodynamics, displacing centuries of supposedly mature practice as described in his very readable book, The Shark's Paintbrush. And he noticed this ropey Fibonacci math structure running down a vortex of, say, water running out of a bathtub. So he cast it, froze it in acrylic, and studied it. And he said, gee, that must be the minimum energy shape that the air-water surface assumes. So in a brilliant inductive leap, he then said, gee, maybe if I want to move liquid with minimum energy, I should make my rotor that shape. With this result, only nature could come up with shapes like that. And he notes, for example, that if your 100,000 kilometers of fractal blood vessels in your body down to the teeniest capillaries had the same design and the same kind of friction that industrial piping systems do, your heart would have to be bigger than your body, which would be quite awkward. But actually, your 1/3 of a kilogram, 1.5 watt heart suffices, because you don't have that much friction in your blood vessels, because nature doesn't do our industrial kind of flow. Nature does laminar vortex flow. And take the rotor at the upper left. Let me show you a practical application. Waterworks typically have a big tank, maybe 15 million liters, of water about to be sent out to customers, but they have to keep it circulating so that chlorine or other disinfectant remains active so the water stays safe to drink. And normally that's done with the gizmo on the left. Don't even ask how much energy it uses. Actually, the one in the middle, using that biomimetic tulip rotor on a 50-watt motor, is one of our ex-interns now with the company, does a better job because it sets up ring vortices that maintain themselves with practically no energy. And since these biomimetic rotors' performance does not depend on scale or on Reynolds number, wow, there is even more than we thought to be saved in the 30% of global electricity that runs pumps and fans. There's also a powerful point about where to set our system boundary. General Eisenhower said if a problem is too difficult to solve, enlarge it. Don't cut it into little bite-sized pieces. Instead, move the boundary out until it encompasses what the solution requires. More options, more synergies, more degrees of freedom. It's also become fashionable in many design schools to teach that design is the art of compromise and trade-off, as if it were a way to negotiate with yourself to keep you from getting what you want. But my friend Jay Baldwin was once staring out the window in a California classroom where he was being taught this nutty idea. He was watching a pelican catch a fish. He said, wait a minute, what this lecturer is saying cannot possibly be true. Nature does not compromise, nature optimizes. That pelican, he said, is not a compromise between a seagull and a crow. It's a really good pelican after 90 million years. So if you find yourself needing to compromise between desirable design goals, it typically means you haven't quite found yet the right statement of the design problem. Keep at it, you'll get there. And when you do, you will find, as David Oakey did one day designing carpet at Interface, that you get every outcome you want, none you didn't want, and a bunch of wonderful stuff you never thought to ask for. The hard part isn't the answer, it's the question. Once you find the right design question, the answer is self-evident. So, having spent the past few decades developing integrative design in our little Black Swan hatchery, my colleagues and I are now hatching a plot currently called Tenexior, or Factor 10 Engineering, for, to put it a little impolitely, the nonviolent overthrow of bad engineering and bad design. Because we run around the world, 60-odd countries, observing and helping fix buildings and vehicles and factories and so on, and we see the same design mistakes everywhere. Same kinds I've been talking about, because they are widespread in our textbooks and our classrooms. And if we don't extirpate disintegrated design at its root in pedagogy, we are condemning our successors to perpetual retrofit of inefficient stuff. Not a worthy legacy, not a good use of their time. So we're seeking students, teachers, practitioners who want more of the sort of content that I briefly summarized. There's more of it in these two short papers, who can help us keep improving the content and examples and methods so they go viral and become the norm, not the exception. We are therefore exploring with Olin and Stanford and some other great schools how we could help with and learn from such efforts. Three of us have been here the last few days discussing with Olin students and faculty some potential collaborations. That's been encouraging. I would very much welcome your counsel about what we should do and how. And we want to help also in a larger context while building on your pedagogic success and helping deepen it. I want to help retread the in-practice design professionals and the tradespeople who de facto end up designing a lot of stuff, even if they may not be formally trained in design, pipe fitters, HVAC contractors, and so on. We're also exploring with a major software tool maker how new design software can make better easy. Our Chinese partners have asked us to help inject integrative design vigorously into their new and retrofit buildings and factories all over the country. They have networks for that. And we're looking for an iconic CEO who might eventually want to do for 10xe the sort of promotion that Jack Welch did for Six Sigma, making it a gotta have that in business. And I hope you will suggest other ways that we have missed to help launch an irresistible movement to make design holistic, integrative, super efficient, valuable, and fun. Let me end by illustrating how design has profound human consequences. Today's energy revolution, like many others, depends critically on design, and most of all for the 1.2 billion people with family income around $2 a day or less, and little prospect of getting or affording grid electricity. And those impoverished people are paying $38 billion a year, 1/5 of global lighting services total cost, to buy kerosene for very inefficient lamps that produce 1/1000th of the world's light. Now, if those kerosene lamps were a country, they would rank 8th in carbon emissions, plus huge health costs. But now, those 1.2 billion people can banish darkness and teach their daughters and sons to read, thanks to a new class of engineered device which this is a nice example. It's called the Waka Waka, Swahili for shines brightly. State-of-the-art 23% photovoltaics on the front, heat-tolerant lithium batteries in the middle because it's got to sit in the tropical sun all day, very good Dutch control circuitry, and I think 150 lumen per watt LEDs, which will shine this brightly on one day's solar charge for 10 hours, or at a lower setting for up to 150 hours. You can buy or lease the thing from an entrepreneurial woman in your village and finance it through the smartphone that the USB port recharges. It pays back in weeks to months against the kerosene it saves, and it is equivalent to a perpetual annuity giving you a month's extra income per year. So which of those two offerings is more exciting and lucrative and transformational? Which one depends on great engineering, using the most efficient components to make the whole thing small and portable and affordable and effective? Which of these strategies would be right to entrust with your company's fate and with our common future? Choosing and designing such disruptive futures could just save the world. So I want to thank you all for your good work and your kind attention. I look forward to our discussion.